Uh, so far we saw already how sleep is important for our everyday life, and yeah, that the perceived stress and perceived sleep quality metrics are not that aligned with the wearable devices, but however, in the real world, it's not always feasible to always have the contextual information from people, from subjective measures. So we really have to somehow try to figure out how can we actually use wearables to quantify lifestyle, and then when we find out this, then how can we intervene to make the lifestyle better. So first of all, what we have is the wearable devices, as we saw already in the previous talks, and by these we can of course measure, for example, step count or other activity levels, and then we can of course measure sleep. These can be like sleep quality, body battery, or circadian rhythm disruptions, which we can quantify. Then what is important for us is a statistical analysis where we can try to understand the relationship between the measured variables. However, yes, of course, then we have some contextual information either from derived from, for example, calendar data, like if it's Friday or not, and then the weather data, and then we have also these subjective measures, which could be, for example, if we drank alcohol, and as we already know, all these stuff are somehow influencing our sleep quality and how do we perceive the sleep. And then there are other relationships as well. So if we would like to improve our sleep, and maybe we wouldn't like to tell people like, please improve your sleep score, which is like not really possible to tackle, then we would like to find some other way how to improve the lifestyle as it is. So maybe we could try to intervene on the activity levels if we know that these are important for the sleep quality on the next day. So how can we do this with the digital solutions? We can, of course, send some notifications or intervene in this kind of way. So how could this personalized message look like? What we have as a data could be, for example, the number of steps which person did. Then we have some target which they should do, which is recommended, for example, by the doctor. And we can combine it into the sentence, you did just 5,000 steps out of 10,000 steps a day. This is called biofeedback, and it works for some people not. Then we know, for example, for this person from the conversational interface that this person has a dog, for example, and then we also know that it's a nice weather, which we know from the background data. So we can again combine those. How about taking your dog for a walk? So it's like a push to go do something. This is called the context part of the personalized message, and then we can use for example, one of the Cialdini's 6 persuasive principles. As an example, your doctor recommends you to walk more to improve your sleep. Then we can somehow also look at how can we, because this wouldn't work for everyone, but I would like to focus in this talk more on how can we choose it in a correct way and how can we adaptively find out, because we cannot ask a person, hey, would it work for you if we tell you this? I mean, that's unfeasible. So we would like to find out with machine learning. So just to recap what we had from so what we have available. So we have the data, which is the which is the target data, which we want to achieve. Then we have the objective data from the wearables. Then we have, of course, the subjective and subjective data from the conversational interface or digital diaries. And then we have some contextual information derived from the background data. Then we do the statistical analysis, and then we send a suggestion, for example, go for a walk with your dog. And then we send it as a notification. But we are now going to introduce also some machine learning algorithm. In particular, it would be multi-armed bandit, which is an algorithm from the reinforcement learning, where we are trying to test whether something works. So, for example, in this case, I am trying to choose a persuasive strategy which works the best for the person. So this was the authority. As you can see, the small icon of the doctor. So we send such a message, which we've created in the previous slide, and then we check at the proximal outcome. So it would be how many steps the person actually did by the end of the day. If we see that the goal was fulfilled, then we give a reward back to the multi-arm bandit algorithm, which is typically in the reinforcement learning setup. And if the person didn't fulfill the goal, then we just say it didn't work with this strategy so well. If we do this over a long time, so we do this several times for the person, then we gradually somehow learn something about that person. So in a nutshell, how this is done, we have the, so we can use the Thompson sampler, for example. This is the Bayesian multi-arm bandit for personalized persuasive strategy selection, but it could be used also for choosing whether we want to, for example, send the biofeedback, whether we want to use the context, and so on. In a clinical trials, this is called response adaptive randomization. And I will just show you quickly how does it work. So now imagine that we have like 6 of those strategies. The bigger the machine is, the more it is working for that particular person. So for example, the red one would be the most persuasive for you. So if it's sent, there is really high probability that you would actually go for a walk. So that's the point. So we call these strategies, or we call these arms, or yeah, they are arms, the strategies are mutually exclusive, so there is no correlation between them. And the probability, so the assumption is that the probability of success of those strategies are stationary. Of course, this is not true in the real world for a too long setup, but for a shorter time, for example, I don't know, in the last 50 days, for example, it could be true that you are not changing that much that the assumption would be violated. And then, of course, we have the binary reward in this setup, so we could use the Beta-Bernoulli model, which has a nice property of the conjugate prior. But of course, if the idea or if the outcome would be of a different distribution, then we could just change the model. So what would we do? We would start from the flat prior, which would mean that we would have the same probability of each strategy to be effective, and gradually by testing it and then getting the feedback of yes or no, if it worked or not, then we built posterior beta distributions. So the dashed line is the true value of the probability whether it worked for you or not. And the small dots on the x-axis are the sampled, what we sample at this step. And always I choose the strategy which has the higher probability of success. So at this time, I've chosen the black one, which is the authority principle. And by doing this, we can also learn the implicit profile, because this is naturally created by the process. So for example, I can look at the similar people who have similar preferences by looking at their posterior beta distributions. Okay, so was the aim of the system actually achieved? How can we measure that? So first of all, we can look at the target of the daily steps, if it was actually achieved, or whatever was our aim. Either it was like the daily steps as in our example. And then we can have a look at the whole picture, like with the statistical analysis, whether the lifestyle and sleep was actually improved. So yeah, we can use some graph learning techniques to see whether there were some changes for that. And then we could use also the causal analysis to understand whether actually the interventions were helpful as such. For this, typically, we would use the randomized control trial, but in case we do not have enough resources, for example, to have a big enough sample size, we could use also micro-randomized trial, which I will introduce you in a minute. So before I do that, what is the difference between the observational and interventional data? So in the observational data, you have we always have the outcome, which is y, which we define in some manner. So for example, it was the number of steps. And then we have like a treatment. So that would be our intervention on what effect do we actually want to study. So we want to study the effect of the treatment on the outcome. But there is a problem that we have some confounders which are confounding both the treatment assignment and the outcome. How can we deal with it? We can introduce a so-called do operator, which means that we will intervene on the treatment. So that's our intervention. So as long as we know what we are doing and it's not linked too much to the confounders, then we know how can we actually compute the effect in an unbiased way. So from this we can get to the interventional data and we get rid of the effect from the confounders to the treatment, which is actually important for us, and this is how the RCTs work. And we, in the end, compute the average treatment effect, which is the expected value of the difference of the expected value of the outcome under the intervention on the treatment. Okay. How can we use this in the micro-randomized trial if we don't have enough resources for the RCTs? And these micro-randomized trials are typically actually used in the digital intervention settings because you do multiple interventions during the long time on one person. So we have a suggestion, of course. We have the bandit, which is choosing the personalized strategy, and then we have the notification, which we send. But we have to introduce something what we know what we are intervening on. So this would be the random component, where we can at each time point when we want to send a notification, we decide randomly whether we actually send it or not. So by this we introduce the treatment days and the control days for a person, and then we can compute the proximal outcome, which could be either it worked or not, so it could be either binary or it could be even continuous. At that time it would be the number of steps, for example, by the end of the day. And we model this by the treatment component or the randomization and by some contextual information which we know that there they are. So for example, if we want to get rid of the effect of weather, for example, when we know that people tend to walk less when it's raining because no one likes to do activities in outside when it's raining. So we get rid of that effect and we are computing only the effect of the randomization. So then we know that if it was sent, that it was the effect of that treatment actually. And we can do this with a mixed effect regression analysis where we can assess also individual effects by including the random component. Or we could do this only as a regression for one person. Okay, so how is this used in the digital healthcare, especially in the mHealth apps? So it could be used, for example, in the lifestyle to improve sleep, to sleep better, or to improve the circadian rhythms. It could be also used for improving diet, for stop smoking, moving more, and so on. Then in some projects we are also using it in the rehabilitation and the chronic disease management. So it could be, for example, the cardiac, physiological or neurological rehabilitation, where we have patients who really need to improve their lifestyle. And then it could be also in the prevention for example, Alzheimer, burnout, and so on, where the disease didn't develop yet, but we want to prevent it. Of course, and then for the AI coach, for example, for physiologic or for sports. What are the advantages of wearables? I hope by the end of this session you are already convinced that it's somehow good to use the long-term monitoring in a real world setting. So it's really good that we can do the continuous and long-term monitoring, and it could be also important for clinicians to get the insights into the daily behavioral patterns of people. So even though the wearable devices are not they are not perfect, but still, if we would wear them over a very long period of time, then we can really reveal some patterns on a daily lifestyle. Other domains where this framework is used, just like for you to know that it's not developed for the digital mHealth, but rather we adapted it from somewhere else. And it's used, for example, in the educational apps or advertising and news, where they do the A/B testing and they are testing really if it works or not. And then also on the e-shops, where they are recommending you what to buy next. So does it actually work, all these lovely interventions? Yeah, well, as we saw, not every time, because it's, if it doesn't have the contextual information, sometimes it might be a little bit tricky. But as George Box said, and I saw this sentence on several talks already, all models are wrong, but some are useful. So I hope that this framework will be useful for improving lifestyle, at least a little bit, even though if not fully, but yeah, we are on the right track, I guess. Thank you.